people have come up with some pretty good criteria for what constitutes a beautiful result in mathematics. Firstly, it should be simple. It should be very easy to understand. Secondly, the consequences of a result should be very surprising, and it should be difficult to understand exactly why the result's true. Now, thirdly, the result should hopefully connect together lots of seemingly disparate areas of mathematics, a little bit like a bridge that specialists in one area can use to cross into another area. And finally, the result should lead to many generalizations. It should hopefully be like a seed, which can be used to grow many new kinds of theories. Now, Euler's polyhedral formula satisfies all these results in spades. I mean, it's extremely simple. A 5-year-old can understand the contents of this theorem. It's really, really simple. And it is not particularly easy to understand why it's true when you first see it, because it seems like such a general claim. When you initially look at it, it seems hard to understand how one could prove such a general result, although actually there is a relatively simple proof. The result connects together lots of different areas of mathematics, like the ideas of curvature, lots of ideas to do with surfaces, and some ideas to do with combinatorics, and some graph theory. So it connects together lots and lots of areas of mathematics in a very, very elegant way. And finally, the result, I don't think it's too much of an exaggeration to say that this result really almost led to the birth of topology, which is one of the most fertile and important areas of modern mathematics. So this is a truly wonderful formula. Well, okay then. Let's just start with the humble cube. And I want to tell you something about the cube, but it's something which is true of many other polyhedra as well. Here is our cube, and let me start to explain about this polyhedral formula. So, how many vertices, or corners if you like, does this cube have? Well, let's call that number V. Let's just look at the cube. It has 1, 2, 3, 4 vertices in front and 4 at the back. So the number of vertices is equal to 8. How many edges does it have? It has 4 on the front, 4 on the back, and 4 which are kind of pointing away from us. And so it has 12 edges. How many faces does it have? Well, anyone who's played with a dice will know that it has 6 edges. So there's a special relationship between these numbers. In particular, the number of vertices, take away the number of edges, plus the number of faces is equal to 2. Let's just check. 8 minus 12 is minus 4, plus 6 is 2. Okay, so is this a coincidence? No, this is not a coincidence at all. This is Euler's polyhedron formula, and it holds for every single convex polyhedron. Pretty much every polyhedron that you think of. They don't have to be regular. This just holds for an amazing array of objects. And the edges don't have to be straight. They don't have to be the same length. For example, if you have a look at the shape of a house with a roof on it and such, if you count the number of vertices, edges, and faces, and vertices take away edges plus faces, the result will be 2. This is a very, very general formula. Okay, so I want to show you some applications of this formula. So here are some different convex polyhedra, and for each one I've given the name, the number of vertices, edges, and faces, and check that this result holds. The number of vertices take away the number of edges plus the number of faces equals 2. So look at all these different polyhedra. The dodecahedron, that's a famous one. There are some ones which are perhaps less well known to you, but in each of these cases, Euler's polyhedron formula, this, holds. It holds for every single convex polyhedron. Now, what do I mean by a convex polyhedron, you might ask? Well, technically, we say that a polyhedron is an object that you get by sort of gluing together a load of polygons to make a kind of closed object, something like a sphere, for example. And we say that such a thing is convex when for every pair of points on the polyhedron or in the polyhedron, if you draw a line between those points, then that line will always be contained within the polyhedron. So, for example, if you make a kind of L shape with 2 rectangles, that would not be a convex polyhedron. But all of these are convex, and Euler's formula holds in every single case. Now, I tell you one of the things I find most remarkable about this result. And it's kind of it's slightly offensive, but I really find it remarkable that the Greeks didn't discover this. I mean, the Greeks, especially sort of great mathematicians like Archimedes, studied polyhedra so much, but they never seemed to notice that every single convex polyhedron satisfies this lovely little formula. Now, these examples which I'm showing you are all quite special. The vertices are regular, and the edges all have the same lengths, and all the edges are straight, but in fact, none of these criteria have to be satisfied in order for Euler's formula to work. It's a much more general result. Well, okay then, so here's another network, or graph if you like, that's drawn on a sphere. And notice that this is not actually a polygon in the strict sense. But we can see that Euler's result still holds. How many vertices does this thing have? Well, it has 1, 2, 3, 4 vertices. How many edges does it have? 1, 2, 3, 4, 5 edges. How many faces does it have? Well, it has 1, 2, and an exterior, so it has 3 faces. So once again, V, take away E, plus F, that's equal to 4, take away 5, plus 3, is equal to 2. Euler's result still holds. So Euler's result holds for every single graph which is drawn upon a sphere. And it turned out that when Euler discovered this result, he had quite a hard time proving it, because he was initially thinking in terms of polyhedra. And so to prove it in that kind of framework was kind of difficult. But later on, with the development of graph theory, which, by the way, Euler also kind of kicked off with his study of the Königsberg bridges, when people started thinking more about graph theory, they realized that this formula actually applies to general graphs, and they discovered a really nice simple proof of this result. So I know in this sort of elementary course, I said I wasn't going to do many proofs, but I think that it's worth going through a proof of this result, because it's such a nice result, and I think that you deserve to understand why it's true, and it's not really that hard to follow. I want to give a quick proof of Euler's formula. So let me draw a graph here. It can be any graph at all. And I want to prove that Euler's result holds. So there's loads of different ways you can prove it. I'm going to imagine, rather than imagining this as a polyhedron, I'm just going to imagine that it's some graph which is drawn upon a sphere. So if you'll bear with me, imagine that this is not drawn on a plane, but drawn on a sphere. And so when we think about the different faces of this graph, we have 1, 2, 3 interior faces, and also one exterior face, which corresponds to the rest of the sphere, which this graph has been kind of sketched on.
So what we're going to do is to make a spanning tree of this network. So it's very easy to make a spanning tree. It's basically, okay, so what we're going to start by doing is to draw a spanning tree of this network. It's basically just like a tree which one could use to go between all the different edges, all the different vertices of the graph. So it's very easy to construct a spanning tree of any connected graph. It's always possible. To do it, you just keep every time step, you can just look and see if there's a vertex which is adjacent to a vertex which is not on the tree. And if that's so, then link it by an edge, just so long as it's not already linked by something else, because we don't want to create any cycles. So for example, if we look at this vertex here, we see that it has a neighbour which is not linked to anything else on the spanning tree, so we can draw an edge like that. Now, this has a neighbour which is not linked to it on the spanning tree, but it is linked to something else on the spanning tree, so we don't draw an edge there. But we can draw an edge up here, and we can draw an edge up here, and we have a spanning tree. Now, hopefully you can see that every single graph has a spanning tree, every connected graph. So here we go. Now we've constructed our spanning tree, we can do our proof of Euler's result. So suppose we have this graph. I mean, I know I've drawn a specific graph here, but just suppose it's a general graph. And let's suppose that we count the number of vertices, take away the number of edges, add the number of faces, and we get some number, x. Now, we want to show that x equals 2, but we're trying to prove that, so we're not going to assume it a priori. We're just going to say that it's equal to some number x. Now we're going to do some operations. What we're going to do is we're going to delete some of these edges which are not belonging to the spanning tree. So here's an edge not belonging to a spanning tree. Let's delete it. Now, what happened? Well, we've reduced the number of edges. So what have we just done? Let's write it down. We just deleted an edge. So we've reduced the number of edges by 1. And we've also reduced the number of faces by 1, if you think about it. Because every edge is separating two faces. So when we delete an edge, we cause two faces to merge, essentially. And so hopefully you can see then, if we reduce E by 1 and we reduce F by 1, then this quantity will not change. In other words, after we've deleted this edge, the resulting graph will still have the property that the number of vertices, take away the number of edges, plus the number of faces equals x, whatever x may be. So now we just keep repeating the process. Let's delete another edge, which is not on our spanning tree, say this one. Okay, again that reduces the number of edges by 1 and the number of faces by 1, because these two faces merge. And we can do this again. We'll delete another edge which is not part of our spanning tree. And again, this preserves this fact that V take away E plus F equals X. So finally, we've deleted so many edges that all we have left is a spanning tree. Now it's a tree, that means it's a connected graph with no cycles. In other words, it doesn't have any interior faces. Now, there's something important about trees. The fact is that for every tree, we have this important fact that the number of vertices is always equal to the number of edges plus 1. Now, to see this is quite easy. If you just note that you can make any tree by starting off with a single vertex and then just adding a new vertex with an edge linked to something pre-existing. You can keep doing that to build up any tree you like. For example, if you wanted to build this, you could start off with a single vertex. I'm not sure if I've got enough space, but we can try and do it. Here we have a tree where the number of vertices is 1 and the number of edges is 0. Now if we add another sort of leaf, if you like, a vertex with an edge, again we have V equals E plus 1. Now we can add another leaf, and again V equals E plus 1 because we've added one edge and one vertex. And we can continue like this to construct our original tree. So in general, this result holds for every tree. Okay then, so now we're in a position to actually prove our results. So let's think now about this spanning tree which we've uncovered. Now, we know, because it's a tree, we know that V equals E plus 1. So let me just do a bit of rubbing out. Bigger rubber. Okay. So we know v equals e plus 1. We can substitute that into this formula. We get e plus 1, take away e, plus f equals x equals 1 plus f equals x. So what is f? Well, although our tree doesn't have any interior faces, it doesn't have any cycles, it does have, I ought to have drawn an edge there as well. It does have an exterior face. So the number of faces it has is 1, because it's drawn on a sphere. And so we have that this is equal to 2 equals x. And that finishes our proof, because we've shown that for our original graph, whatever that might be, v take away e plus f equals x, and x equals 2. We've shown that by deleting edges and showing that, as we delete the edges, this quantity is preserved, and we end up getting down to a structure where we find out that this result is equal to 2. So there you have it, that's a proof of Euler's theorem. The ancient Greeks discovered the Platonic Solids, very, very important thing in the history of mathematics. And they found out that there was only 5 Platonic solids, and the proof that they used was relatively complicated. But with Euler's formula, we can see it almost immediately. So the 5 Platonic solids, the cube, dodecahedron, icosahedron, octahedron, tetrahedron. Now, these Platonic solids have the property that every vertex has the same number of edges incident upon it, and every face has the same number of edges which are around it. In other words, every face is the same kind of polygon. Now, we can use Euler's formula to prove that there's only 5 Platonic solids. We know that our Platonic solids satisfy the Euler's polyhedral formula, meaning that the number of vertices take away the number of edges plus the number of faces equals 2. Now, we also know some other things. Let's say that for a particular Platonic solid, that every face has S edges. Well, then we know that S F equals 2E. Why is that? Well, imagine counting over all the faces, and for each face we just count how many edges there are touching that face. And so if we do that process, we're going to count the number of edges, but we're going to count every edge twice, because every edge is incident upon 2 different faces. So that's why the number of faces times the number of edges a face has is equal to twice the number of edges. Since this is a Platonic solid, every vertex has to have the same number of edges incident upon it. So let's say that M is the number of edges touching every vertex. So we have a similar result. We have that MV equals 2E. And again, to see this, note that if we just add up over all of the edges, and every edge if we add up over all the vertices, and every vertex has m edges incident upon it, then we can just add up all the edges that we see by looking at every vertex and looking at the edges which are touching it. And if we do that, we're going to count v times m edges, but we're actually going to have double counted the edges because we'll have counted them once from each of their terminals. And so we get that the number of vertices times the number of edges touching each vertex is equal to twice the number of edges. So now, to find out that there are 5 Platonic solids, it's kind of like a bit of magic. All we have to do is substitute these expressions into Euler's formula and we'll get the result. So, in particular, we can rewrite these equations as f equals 2e divided by s, and v equals 2e divided by m. Okay, so we can substitute these expressions into Euler's formula. So we get that 2e, excuse me. Okay, so we can substitute these expressions into Euler's formula. So substituting for v, we get 2e divided by m. E stays the same. Substituting for f, we get 2e divided by s. And that's all equal to 2.
And so what we have here is what's known as a Diophantine equation. What it means is it's an equation and we're looking for solutions which are integers. In our case, positive integers. I mean, the number of edges, e should be a positive integer, the number of edges which touch every vertex should be a positive integer, the number of edges in every face should be a positive integer, that's s. So we're looking to find positive integers e, m and s which satisfy this equation. Now you can look at this and you can find the solutions. I'm going to leave it as an exercise for you to do because I think it's rather worthwhile. You will find more than 5 solutions, but if you then go back and check what they mean graph theoretically, you'll notice that some of them don't actually correspond to proper things. So in the end, you get your 5 proper solutions corresponding to the 5 Platonic solids. And I think this is a really worthwhile exercise to do because, let's face it, these Platonic solids are very, very special, almost kind of magical objects. And it's worthwhile sort of seeing why there are only 5 of them. And all you have to do is solve some integer equations, which is a kind of fun number theoretic exercise anyway. Okay, so another great thing about Euler's formula is that it can get you out of some really fiendish unsolvable problems. So if you have an evil mathematical friend who gives you a puzzle like this, where you have a water plant, an electricity station, and a gas station, and 3 houses. And your friend asks you to try and link these things up without any of the edges crossing. You will find that it is not possible. And usually people say things like, oh, try and link them up without crossing any edges. But it's absolutely impossible, and you can waste decades of your life trying to solve this problem, because there's just no way to do it if you're only working on the plane or the sphere. But thankfully, armed with Euler's Formula, one can actually prove that this puzzle cannot be solved. Okay, so here's where things start to get really interesting. And here's where we start to see where this Euler polyhedral formula can be extended to tell us loads and loads of things about the topology of surfaces. So, as I say, this water, gas, electricity problem is unsolvable. You can't link up the water, the gas, the electricity to these three houses without some of the lines crossing if you're working in the plane. But look at this picture here at the top right. Now, this shows that the problem is solvable when you're working not on the plane, but on the torus. Okay, just to be consistent, I better label my houses 1, 2, and 3. But yes, this problem is solvable if you're working on a torus, that is a donut shape. Okay, so I'm going to try and draw some sort of torus shape. So far so good. These are the connection points. And again, blue this time. So to finish this drawing off, I think we just need one more edge. And there we have it. We have a graph drawn on a torus. And so now we can work out what our different numbers are, counting the number of vertices, faces, and edges. So let's go. The number of vertices, that's quite easy. That's just 3 times 3, is 9. The number of edges, a little more challenging. That's 3 edges between each pair of circles. So that's 3 plus 3 plus 3 is 9. and also 3 edges on each circle. So that's also plus 9. And now for the number of faces. Well, we've got 1, 2, and a third external face there. Similarly here, 1, 2, 3. Similarly here, 1, 2, 3. So we have that the number of faces is again equals 9. So what we find out in this case, interestingly, is that V, take away E, plus F is equal to 0. Now isn't that interesting? When we have a convex polyhedron with no holes in it, every graph that we draw on it, the number of vertices take away the number of edges plus the number of faces equals 2. But when we have a graph with a hole in it, we get that quantity instead equals 0. And this is actually a kind of sort of the tip of the iceberg. This is part of a much more general result, which I'm now going to tell you in totality. Basically, different surfaces have different Euler characteristics. The Euler characteristic of a surface is equal to V take away E plus F. And so you can express it like that in terms of a graph that you draw on the surface. We can also express it in terms of the genus of the surface, where the genus means the number of holes. So the sphere has genus 0, the torus has genus 1. Okay, and so what I've been trying to convey is that this idea that follows from the Euler polyhedron formula is actually quite a lot deeper. So, in particular, if we have a graph drawn on a closed, bounded orientable surface, so, in other words, something that looks like maybe this, like something like a sphere or something with some holes in or something like that. If we have something along those lines and we take the number of vertices minus the number of edges plus the number of faces, well, we call that quantity the Euler characteristic. So we can speak of the Euler characteristic of polyhedra, because a polyhedron basically is kind of like a graph drawn on a sphere. I mean, it has edges, we can think of the faces and the vertices, etc. We could also think about perhaps something like a coffee cup as being some kind of solid with edges and faces and vertices and such, which is actually embedded on a torus, and so on and so forth. So all of these closed orientable surfaces can be associated with an Euler characteristic. Now, I just try to convince you that when we're on a sphere, we always have that V take away E plus F equals 2. So for every graph embedded on a sphere, what you'd say is that the Euler characteristic associated with a sphere is always equal to 2. But more generally, it's equal to 2 times 2 times the genus. Sorry, 2 take away 2 times the genus of the surface. What's the genus of a surface? Basically, it's the number of holes. So the sphere has genus equal to 0. This one-hole torus has genus 1, this has genus 2, this has genus 3, and so on and so forth. Now, there's something that I think's a lot more interesting going on here as well, and that is a connection with curvature. So there's something called the Gauss Bonnet Theorem, and in a nutshell, what it says is this. It says that, well, hang on. Let me first explain a little bit about what curvature is. So, if you're doing geometry on a plane where everything's flat, you get the normal kind of geometry where the angles of triangles add up to 180 degrees and so on and so forth. But if you're doing geometry on a sphere, things can be quite different. For example, if you start at the equator and you go to the North Pole, and then you turn at right angles, and you go back down to the equator, and you turn again at right angles, and you go back to where you started from, you just traced out a triangle which has 3 right angles. And so that shows that spherical geometry is fundamentally different to planar Euclidean geometry. Now, the reason for that is because the sphere has positive curvature. And in particular, this is a consequence of, in a sense, the Euler characteristic. So this is something really amazing about the Euler characteristic. Not only does it help you to describe the topology of the surface, not only is it some unifying fact which lies behind all polyhedra, it also tells you about the curvature of the polyhedra. So we have the Gauss Bonnet Theorem, which in a nutshell basically says that the total curvature of a surface is proportional to the Euler characteristic. And so we have that since the sphere has a Euler characteristic of 2, it has positive curvature. Since the torus has Euler characteristic of 2 minus 2 equals 0, it has 0 curvature. And that actually means that the torus, in a curvature kind of sense, is quite like the plane. And you can kind of understand that, because if you think about what it's actually like to live on a torus, I mean, we can represent a torus like this by gluing the top to the bottom and the left to the right. So say we had a cross here. Well, what it would actually look like if you're walking around on this torus is it would just look like you'd see a cross here, and then you'd see another cross here, and you see another cross here, and so on and so forth. So basically, if you're walking around on a torus, it's sort of like walking around on flat planar space, and that's why it has a curvature of 0. And if you draw triangles on a regular torus, you'll get 180 degree summation of the angles. So let's make this more concrete. The Euler characteristic for the sphere is equal to 2. That means the sphere has positive curvature. That's why spherical geometry has certain attributes, which I discussed in another video, by the way. The torus has Euler Characteristics 0. It has 0 curvature. It has similar kind of geometry to a plane. The double torus has an Euler characteristic of -2 because it has genus 2. So that means that this double-hole torus is very special, actually, because it has negative curvature. So what that actually means is that essentially, if you have a sort of regular double-hole torus, you've got hyperbolic geometry upon that. And again, I discussed this more in another one of my videos, but it's quite fascinating to think about how when you take a surface, as you make more holes in it, as you increase its genus, you get something which has negative curvature. And that allows you to do lots of interesting things, like you can draw all kinds of networks and tessellations on these kind of tori with many holes that you could never do ordinarily. So if you've seen about hyperbolic geometry, you'll notice that in hyperbolic geometry there's a huge number of regular tessellations, and you can create stuff like that when you've got these shapes which have lots and lots of holes in them, these high genus shapes. By the way, I should probably just give a rigorous definition of genus. So we're thinking of these surfaces as like shells, you know. So our sphere, we don't think of it as being full. We just think of it like a balloon or something. So we're just thinking about the external surface. Now, the genus of a surface is formally defined as the, what is it now? As the maximum number of closed loops which you can cut out of your surface without disconnecting it. So in a sphere, the genus is 0, because if you cut out any closed simple loop, you end up cutting a piece out of the sphere which disconnects it. On the torus, on the other hand, if you cut out a closed loop which goes something like this, then it doesn't disconnect the torus, but then the second closed loop would. So that has a genus of 1, and so on and so forth. Okay, so this is really the fundamental point of the lecture. The connection between counting vertices, edges, and faces, counting genus, and determining curvature, which determines geometry, be it Euclidean or non-Euclidean. So that's pretty much all I wanted to say, but I want to end by talking about something which is a bit more fantastic, which is about high dimensional generalizations of this idea. Okay, so then those of you that have seen a fair amount of mathematical notation before might be confused about why I have been writing the Euler characteristic as I do. I mean, I write it like this. Euler characteristic equals number of vertices, take away number of edges, plus number of faces. So, I mean, I know it's a pedantic point, but it did bother me when I first saw this in textbooks, I often wondered, why don't they write it like this? Why don't they write it as V plus F take away E? I mean, it's traditional to have the negative bit at the end. And it turns out there's actually a really good reason for this original notation. And that is that the Euler characteristic actually extends to high dimensional spaces. So if you have what are called cyclical complexes, which are essentially like, I'm going to speak in rough terms now, okay? I'm not going to be precise. Essentially, they're kind of like high dimensional versions of surfaces. And so basically, we can write things like this. We can write like C0, and that can be a zero-dimensional object. That's a point. Okay, and then C1, it's a one-dimensional object. That can be an edge. C2, two-dimensional object. That can be a triangle. But just for now, let's be more general. Let's say it's a face. And we can go on. C3. That can be a solid, like a sphere. And even we can go on, C4 can be a hypersphere, etc. Now, it turns out that this whole result generalizes. So, in fact, what we end up getting is that for more general kinds of cyclical complexes, we can define the Euler characteristic as equal to this alternating sum. So it's C0 take away C1 plus C2 take away C3 plus C4, etc. And there we have it. And this is a topologically invariant property. It's an interesting way to understand the topology of these high dimensional things. So the Euler characteristic tells us almost everything we need to know about surfaces, and it generalizes to higher dimensions.